Hello, everyone. Welcome to the April 16th edition of Math 371. I hope you're doing well today. Quick reminder that online homework is due on Friday. So last time we talked about eigenvalues and eigenvectors, and eigenvectors are easy to find once you know the eigenvalues. And the eigenvalues are obtained by finding the roots to a certain polynomial. So one question that remains is, which matrices have the same eigenvalues? It's a very good question, and we're going to investigate it. But first, we need a couple definitions. So if A and B are n by n matrices, then we say that A is similar to B if there is an invertible matrix which we typically call P, such that P inverse times A times P is equal to B. All right. So changing A to P inverse AP is called a similarity transformation. Okay. So matrices being similar is what's called an equivalence relationship. If you've seen logic and sets, you've seen it there. And so in abstract algebra, we'll talk a little bit about that with respect to matrices. So we have a theorem, and the theorem is that if n by n matrices A and B are similar, then they have the same characteristic polynomial and thus the same eigenvalues. Okay. So let's prove this. It's very easy to prove. So let's say that B is equal to this lovely expression right here. So what this tells us is that B minus lambda I is the same as P inverse AP. Excuse me, I wrote that down wrong up there. And we subtract off lambda I. Well, I is just equal to a matrix times its inverse. And now we can factor. We can factor out a P inverse on the left and a P on the right. So now we want to take the determinant. The determinant of B minus lambda I is the determinant of P inverse times A minus lambda I times P. And we know that the determinant is multiplicative. And we know that the determinant of a matrix and its inverse are multiplicative inverses. So they multiply together to be 1. And so we get the determinant of A minus lambda I. And so we see that A and B have the same characteristic polynomial. All right. There's a warning though. And the warning is that matrices with the same eigenvalues are not always similar. So for example, let's take the matrix of all zeros and the matrix with a 1 in the top right. These both have the same eigenvalues. They both have eigenvalue 0 with multiplicity 2. But if I try to multiply this matrix on the left by anything, no matter what I get, I'm going to get the 0 matrix. So that means that there's no way that these matrices can be similar. All right. So that's section 5.2, and we'll see these concepts coming up more in 5.3. So what are your favorite kind of matrices? Your favorite kind of matrices, well, I don't know if you know this, but they're diagonal. So diagonal matrices are great. So what are some examples of diagonal matrices? Well, I think we all know some examples. They're matrices that only have non-zero numbers on the diagonal. You can have zeros on the diagonal, but everything off the diagonal must be 0. So let's do an example where we let d equal 2, 0, 0, negative 1. I want you to find d squared, d cubed, and d to the 20th. Okay, so pause your video, calculate it. It's very easy. Okay, now that you've done that, I think you've found that this is 401, this is 8001, and this is 2 to the 20th, 001. It's very easy to multiply a diagonal matrix by itself because you're just multiplying the entries on the diagonal. So let's look at a situation. I'm going to have you calculate something. Let's let p equal 5, 7, 2, 3, and let d equal 2, 0, 0, negative 1. Let's let a equal p, d, p inverse. Okay, so I don't know what a is, but it doesn't really matter. Let's try to find a to the 10th. So I want you to take your, pause the video, and try to calculate it. Well, it's probably not very easy, but let's try to write down the following. A to the 10th looks like this. So if I'm multiplying it out, I get p times d times p inverse times p times d times p inverse times p times d times p inverse all the way times p times d times p inverse. Now matrix multiplication is associative, so you can multiply in any order. So these matrices multiplied by the identity, so they cancel out. And these cancel out, and these cancel out, and all we're left with is p times d to the 10th times p inverse. So this matrix should equal 5, 7, 2, 3, d to the 10th, which is just 2 to the 10th, 0, 0, 1, and p inverse, which you can check is actually just equal to this right here. I'm not going to multiply out because that's not the point. The point is this. Knowing that a matrix, in this case it was A, is similar to a diagonal matrix makes it very easy to compute A to any power. And we saw that just then. It's very easy to raise it to a power if we know that it's similar to a diagonal matrix. And that is actually an important definition. We say that a square matrix A is called diagonalizable. Yes, it's a real word. If A is similar to a diagonal matrix. Okay. And there's a theorem that's going to go along with that. So an n by n matrix is diagonalizable if and only if A has n linearly independent eigenvectors. In fact, A is equal to P dP inverse with D a diagonal matrix if and only if the columns of P are linearly independent eigenvectors of A. In this case, the diagonal entries D are eigenvalues of A that correspond to the columns of P. Okay. So the proof is important, so we're going to do it, and it's actually very easy. The basis, but we're going to give you a definition first. The basis referred to above is called an eigenvector basis for Rn. Okay, so let's do the proof. We do proofs because it helps you understand why these things are true in general. You know, I know you guys can just memorize some statements and reapply them. That's not the point. The point is to try to understand why things work in an abstract setting, because the hope would be that you can then convey this information more readily to someone else. So let's suppose A is diagonalizable. Then what we see is that P is some matrix with these vectors in it. Okay. And we know that P d P inverse equals A. Okay. So let's look at this matrix PD. It's equal to P times these numbers. Okay. So we notice that PD is P times this If you track this, you're going to find that you get lambda 1 times v1 is the first column, lambda 2 v2 for the second column, and lambda n vn for the last column. So if you do a little algebra, you're going to find that PD times P inverse VI is going to equal lambda VI, which tells us that AVI equals lambda I VI. And so you see that these are the eigenvalues of A, and the vectors are the eigenvectors of A. And we know that P is going to be invertible, and so we know that they're linearly independent. Okay, so here's the process for diagonalizing a matrix, if it's possible. First thing you do is find the eigenvalues. Then you need to find n linearly independent eigenvectors. Then we construct P from those eigenvectors. We construct D from the eigenvalues. And we check that A is PD P inverse. Okay, so let's do an example. I'm going to do an example for you. That way you can figure this out. So let's do this process right here. 4, 0, -2, 2, 5, 4, 0, 0, 5. So the first thing we do is we need to find the eigenvectors. So we need to take the determinant of 4 minus lambda, 0, -2, 2, 5, 4, 0, 0, 5. Sorry, minus lambda, minus lambda. So we expand on the bottom right, the bottom row. Most of them are zeros, and we get 5 minus lambda times the determinant of this lovely expression right here. And that determinant is pretty easy. We get 5 minus lambda, 4 minus lambda, 5 minus lambda. So we get 5 as an eigenvector with multiplicity 2, and we get 4 as an eigenvector. Sorry, eigenvalue. Now we need to find the eigenvectors. So let's do lambda equals 4 first. That's the easier one. And we subtract off 4 from the diagonal. And then we're going to have to solve the homogeneous system. Now we need to row reduce. So this row reduces, let's switch some columns around. So that's, we see through some row reduction. Okay, and that row reduces to 1, 1/2, 0, 0, 0, 1, 0, 0, 0. So what this tells us the eigenvectors are that x3 is 0, x2 is free, and x1 is negative 1/2 x2. So an example of such an eigenvector, we'll call it v1, is the eigenvector, let's do negative 1, 2, 0. So I'm going to check that this works, but I'm relatively confident given our setup. So we get negative 4. See, 10 minus 2 is 8. And then this is 0. So you see this is 4 times v1. All right, now let's do lambda's 5. Yeah. So we take our matrix and we subtract 5 times the identity. We row reduce. We see that this just cancels out. So we see that x2 and x3 are free, and x1 is minus 2x3. So we get minus 2x3, x2, x3 is x2 times this vector plus x3 times this vector. So these should be maybe our v2 and our v3. And let's just check that they work as eigenvectors. That one works. And that one works as well. So we see these are both eigenvectors with eigenvalue 5. So what this tells us is our matrix P should equal, we just take the vectors we just found. We take the vector negative 1, 2, 0, the vector 0, 1, 0, the vector negative 10, 0, 5. So what this should tell us is D should equal 4, 0, 0, 0, 5, 0, 0, 0, 5. And if we did all our math correctly, A should equal P times D times P inverse. And I'll have you check this. This brings us to an important theorem. Now, not all matrices are diagonalizable, but an n by n matrix with n different eigenvalues is diagonalizable. So it's actually pretty easy to show. From section 5.1, you actually know that vectors with distinct eigenvalues must be linearly independent. And if we have n linearly independent vectors in Rn, they must be a basis, and therefore A must be diagonalizable. Okay, so this brings up the question of repeated eigenvalues, like we saw in our example. The eigenvalue 5 had multiplicity 2. So matrices with repeated eigenvalues may or may not be diagonalizable. Sometimes it just doesn't work. And it's complicated. you need something called Jordan form to really address this, and you need the complex numbers. So for example, the matrix, identity matrix, is diagonalizable because it's already a diagonal matrix. But this matrix is not diagonalizable. For part of your homework, I want you to show that this matrix is not diagonalizable by showing the eigenspace corresponding to 1 is not two-dimensional. Okay. So now I'm going to have a couple problems for you to do. So I want you to work on the following example. I want you to diagonalize the matrix 4, 0, 0, 0, 0, 4, 0, 0, 0, 0, 2, 0, and negative 1, 0, 0, 2. And I want you to construct a 2x2 matrix that is diagonalizable, but not invertible. Let me know if you have any questions, and I will see you in class.